All right, Miss Teasley here. We are wrapping up our unit on exponential and logarithmic functions. All right, this section is applications and models of exponential growth and decay. So we have in this box exponential growth or decay function here. Let me circle this. All right, so let y sub 0. So that's just that just represents the initial amount. They like to use a subscript. So y sub 0 is initial amount. All right, so this is the initial amount, and it says the amount or number present at time equals 0. So again, initial amount. Then it says under certain conditions, the amount present at any time t is modeled by this function. So you have the e, which we've seen before, k is a constant, and t is your time. So first example, all right, this is a very, very short section. So this is a growth function model. It says, according to the U.S. Census Bureau, the world population reached 6 billion people during 1999 and was growing exponentially. By the end of 2010, the population had grown to 6.947 billion. The projected world population in billions of people t years after 2010 is given by this function. So this function is t years after 2010. So part A says, based on this model, what would the world population be in, that should be 2010. All right, so 2010, right, that's what this function represents, t years after 2010. 2010 is the initial amount, which is the 6.947 billion. All right, I'm going to actually work it out. This doesn't require any work, but remember, the initial amount is the time, is the amount at time equals 0, when t equals 0. So if you take this function, right, so when you take this 6.947 e, and then you have 0.00745, that's the rate, and then the time would be 0, so times 0. Well, anything multiplied times 0 is 0, so 6.947. Let me move this over a little bit. So I'm going to come this way. So when I get to this next step, when I multiply that exponent, I get 6.947 e. 0 times that decimal is just 0. E to the 0 is just 1. So 6.947 times 1 equals 6.947. So really there's no work required. If you look at the function that they give you, the initial amount is there. It's what's in front of e. Now for the next part, part B, it says, based on this model, what would the world population be in 2020? So if this is 2020, 2020 is exactly 10 years after 2010. So to get my t value, you take the year in question, which is 2020, and you subtract the year that's represented in this problem. So here, oops, so I can back that up. 2020. All right, so it's going to be 2020. So the function says t years after 2010. So to get t, I'm going to do 2020 minus 2010, which equals 10. So when I solve this problem, I'm going to use a t value of 10. So what would the world population be in 2020? So it's 6.947, e 0.00745, and then my t value is 10. So I'm going to put this right into my calculator to get that final answer. So 6.947. All right, then you have your e. So go to your keyboard, e. Exponent. The decimal is 0.00745. So parentheses, because I have to multiply 0.00745, and I have to multiply that times 10. And so I get a value of 7.48 billion. Okay, so 7.48 billion. 7.48, and this is billion of people. So if this trend continues, approximately when will the world population reach 8 billion? So here they actually give you the actual Y value. They actually give you the value. They want to know when, the time. So what you would do is you take the original function that they give us. So this is f of t equals 6.947 e to that decimal 0.00745t. And so we know that the amount over here is 8. So I have to solve this equation. 745t. So it's an exponential equation. I'm going to have to use logarithms to help me. The first step is that I'm going to have to divide both sides. So let me move this over a little bit. So let me take this, move it over here so I can have some space. Let's see. Maybe I get a little bit of space right here. So first thing I'm going to divide both sides by the 6.947 to get rid of this. So 8 divided by 6.947. Put that in my calculator. Eight divided by 6.947. So you want to use as many decimal places, as possible. Don't round too early. I'm going to use 4 decimal places. So 1.1516. So 1.1516 equals this e to the 0.00745t. My goal is to get this exponent down. Well, in order for me to get that exponent down, I have to get rid of that e in front of it. So I'm going to take the log base e of both sides. Well, log base e is just ln. So you stick a ln in front of both sides. And when you do that on your right side, I'm going to come down here. On your right side, the L and the E cancels each other out. So you're left with 0.00745t. And then I have the ln of 1.1516. To get t by itself, I'm going to divide both sides by this decimal, 0.00745. That cancels out. And so when I put this in my calculator, this should give me a number of years. So let's see. So I have this ln of 1.15. So 1.1516. And then I'm dividing that whole thing by that decimal 0.00745. And so that would be, I'm going to go ahead and round this up because we're talking about a number of years. T is 18.9. So T 18.9, which rounds up to about 20 years. The question says, if this trend continues, approximately when? So when, what year? So remember, this formula represents the number of years after 2010. So I take 2010, I add 20 years to that. 2010 plus 20 years is the year 2030. So 2030. All right, that's the year 2030. That's the population. All right, decay function. So we have a half-life function. So this is half-life. Blank is the amount of time. So half-life is the amount of time it takes for a quantity that decays exponentially to become half its initial amount. The half-life formula is y equals a 1 over 2 t over the half-life time. Okay, so a is going to be your initial amount. 1/2 is that decay factor. T is going to be the time divided by whatever the half-life time is. So looking at this example here, the last example, suppose you have 800 grams of a radioactive substance. All right, so it's present initially. And then 2.5 years later, you only have 400 grams remaining. So 800, 400. 400 is exactly half of 800. So that means that this substance has a half-life of 2.5 years. So the half-life is 2.5 years. So that means that in exactly 2.5 years, you're going to have half of what you start with. So it says determinant exponential equation that models this decay. So y equals a, which is the initial amount. So a is my initial. So a is 800. 1/2. We don't know t because they didn't give us a specific t, but we do know the half-life is 2.5. So this is the half-life equation that models this situation here. Now to answer the question part B, it says how much of the substance will be present after 4 years? Well, you know after 2.5 years, you're only going to have 400. So in 4 years, you should have less than that. So using this formula, y equals 800, 1/2. The time, our t value is 4, and you have to divide that 4 by 2.5. I'm going to put this in my calculator to get my answer, my approximate answer. So 800, parentheses, 1 divided by 2. Exponent. You have a fraction in your exponent, so you want to put parentheses. The time is 4. We divide that by the half-life time, which is 2.5. So you'll have approximately 263.9. So 263.9, all right, which if they ask you to round to the nearest whole, it would be equal to 264 grams. All right.